Hi, good afternoon. Welcome to continue the electromagnetic wave theory, where in the last session we stopped what are the basic variation of the electromagnetic wave function with the differential operator del. Let us go applying differential operator del, and we have to design the very important two theorems called as Stokes theorem and Divergence theorem. What is Stokes theorem? What is the importance of Stokes theorem in physics or mathematics? You have a line integral, and that line integral is converted into surface integral. So the conversion of line integral to surface integral or surface integral to line integral is done mathematically with the help of Stokes theorem. The second one, Gauss Diverges theorem, will convert or relate between surface integral and volume integral. Means which converts surface integral into volume integral or volume integral into surface integral. This will help to explain electromagnetic wave fields where it is applicable in the field of radar, communication, or explaining the magnetic fields and electric fields, electromagnetic wave fields, various fields, microwaves. These can be explained with the help of these relations, and hence Stokes defined first statement which gives the relation between line integral and surface integral as the statement of the circulation of a vector function along a closed curve C. Circulation means the circulation of a closed curve C is equal to the flux of vorticity of bounded surface by that closed surface. A closed surface forms some surface area bound, and that surface bound, the flux, a flux from that surface is equal to the line integral of a closed curve C, and that can be mathematically written as line integral E bar dot dl bar is equal to surface integral del cross E bar dot ds bar. This is the statement of Stokes theorem. Let us now go for verifying the Stokes theorem. To verify the Stokes theorem, first we have to assume a closed curve and which forms the surface S. Let a closed curve C which has a vector of E bar. This closed curve C forms a surface area S, and this vector function along any point of the curve is the tangential line, and this is the E bar. And now the closed line integral of a curve C is given by E bar line integral, closed line integral, E bar dot dl bar. This is the closed line integral of a vector function in a closed path. Now assume this closed curve C, where it forms the surface S, is divided into a large number of small surface elements, and this is the ds, this is the ds, all equal parts of surface elements. These equal parts of surface elements have this direction of vector and normal to the surface, hence the direction of surface element is given by n into ds or ds bar, and this vector quantity is a flux from this surface, small surface ds. And now coming to the definition of curl of a vector field, along from the definition of curl of a vector field, the Maxwell line integral along the line integral of vector computed in unit area along the boundary surface is given by curl, that is del cross E bar. So del cross E bar into ds will give the bound flux diverge from this surface ds, which is equal to the maximum line integral of a vector commutative from ds area. So the ds area vector quantity calculated by maximum integral value is curl E bar dot ds bar. If it is applied to the total surface S, then you can write that so surface integrals curl E bar dot ds bar. And now from figure, if you can take that the diagram, in this diagram, suppose if this total curve is divided into two curves, C1 and C2. The curve C1 forms the surface area S1. The curve C2 forms the surface area S2. Let us see the direction of the curve C1. This is curve C1 is traveling along this direction from X to Y. Curve S1 is traveling from X to Y. The curve S2 is traveling from Y to X in this common part, along from Y to X, because the direction is like this. This is S2 and this is S1. Here at the common part XY, the curve C1, curve C2 has common integral value in opposite direction. This common integral value in opposite direction will cancel with each other, thereby no net maximum line integral in this common area, common line. And there only the total line integral of S is equal to the line integral of C1, line integral of C2. That is why we can neglect all the inner common line integral values, and finally we can write that closed line integral of a C is always equal to the curl of a vector field of the closed surface S bounded by that curve C. Hence we can write the line integral of a closed curve C, E bar dot dl bar, is equal to the curl of a vector field, surface integral of curl of a vector field. And hence this relation gives the conversion of line integral to surface integral. This is called Stokes theorem. Let us go to the second theorem, that is Gauss divergence theorem. This Gauss divergence theorem, I already told that it converts surface integral to volume integral. The flux delivered from a closed surface S is equal to the divergence of a vector field of the volume formed by that closed surface. A closed surface forms the volume, and let the volume is V and surface S. And now we can write that from the definition of divergence of a vector field, the amount of amount of flux diverging per unit volume is always given by del dot E bar. So del dot E bar is nothing but the flux diverge from unit volume. The flux diverge from dV volume is equal to del dot E bar into dV. The flux diverge from total entire volume V is equal to volume integral del dot E bar into dV. So this is called the flux diverge from total volume V, and which is nothing but like this. This is the flux diverge from the dV part, dV. Now coming to that, the surface area, the surface area element of a vector function is given by E bar dot n cap and E bar dot ds, which is the surface element of the ds surface, E bar dot ds bar. The surface element of the total surface S is given by surface integral E bar dot ds bar. From the definition, this is the nothing but the flux diverge from the surface S. Previously you have calculated flux diverge from the closed surface S from the volume component as like this. This is volume integral del dot E bar into dV. And now these two equations are equal because the same will represent the flux diverge from the surface, flux diverge from the volume. These two are equal. Hence, this is the verification of a Gauss divergence theorem. Okay. Let's coming to the very important relations where it is to be very applicable in relations called as Maxwell equations. You have to be apply the electromagnetic energies by means of Maxwell equations. And what are the Maxwell equations? The Maxwell equations are derived by the basic principles of electromagnetic theory, and from the electromagnetic theory, Gauss defines that Gauss law, where the amount of electric flux diverges from the volume, defined by the Gauss Flux Law. And similarly, the amount of magnetic flux diverges from the volume. Similarly, Faraday's law, which will give the relation how much magnetic induction is delivered, that is can be given by Faraday's law. And Ampere's law, which will give the amount of current generated with the magnetic field. Relation between electric and magnetic field will be given by the Ampere's law. These Gauss laws, Faraday's law, Ampere's law together forms the four important basic relations were called as a Maxwell equations. Let us see about the Maxwell equations. There are two forms in the Maxwell equations. One is integral form, other one is differential form. We have to take the integral form first, and from the help of basic mathematics, we will convert that into differential form. Let us take first Maxwell equation. First Maxwell equation is derived from Gauss Flux Law. What is Gauss Flux Law? The amount of flux diverges from a volume. The amount of flux diverges from a volume is equal to 1 over epsilon times the charge. So the amount of charge is Q, and 1 by epsilon naught multiplied with the charge Q will give the flux phi, and hence the flux phi is along a closed path is also given by, from the definition of flux, surface integral E bar dot dA bar. And this is the equation 1, this is equation 2. These two equations are made equal to each other. Surface integral E bar dot dA bar is equal to Q by epsilon naught. This is called integral form of Maxwell equation, first Maxwell equation. Let us go for differential form. From the Stokes theorem, Diverges theorem, we can convert the surface integral into volume integral. So E bar dot dA bar can be converted into volume integral by writing del dot volume integral del dot E bar into dV, and right side part is as it is, and hence the right side part is rho dV, and left side part del cross E bar into dV, and line integral del dot E bar is taken outside. Here this side Q by epsilon naught, rho by epsilon naught is taken into other side, where we have get the integral dV is get cancelled on both sides, hence del dot E bar is equal to rho by epsilon naught. This is called Maxwell first differential equation. Maxwell first equation in differential form. Del dot E bar is equal to rho by epsilon naught. Line integral, surface integral E bar dot dA bar is equal to 1 over epsilon naught. Integral rho dV is the integral part. And let us come to the second Maxwell equation. The second Maxwell equation is defined from the Gauss Flux Law of magnetism. According to Gauss Flux Law of magnetism, the flux diverges from a closed surface is equal to the 0, because the magnetic flux does not travel from one pole to the other pole. Only monopole is existent. That is, monopole does not exist. That is why we can write integral of B bar dot dA bar is equal to 0 is the integral form of Maxwell second equation. The differential form is converted, this surface integral is converted into volume integral with the Gauss Flux Law as volume integral del dot V bar dV is equal to 0. Del dot V bar is equal to 0 is the differential form of second wave equation, second Maxwell wave equation. So del dot E bar is equal to rho by epsilon naught, del dot V bar is equal to 0 is the second Maxwell equation. Thank you one and all.